Welcome to the course on fundamentals of MIMO wireless communications. We are currently studying correlation properties of the received signal when continuous wave is transmitted, and what is received, what we have seen is randomly fluctuating amplitude. We have seen its distribution, and we have also derived the expression for the correlation of the I component. So what we have last derived is the autocorrelation of Hi which with a lag of delta t is omega p by 2 pi 0 to pi cos 2 pi fm delta t sin theta d theta, and this turns out to be the Bessel function of the first kind of 0th order. So this is where we had stopped our last discussion, and to complete the description, we also need to write the expression for phi hq hi. Now looking at the expression for hi hq, we can more or less guess what will be the hq hi, that is the correlation of the cross components. Minus pi to pi, instead of cos, what we have is a sin 2 pi f max delta t cos theta d theta, and for cos we got this j0, but whereas for sine, since it is an odd function, this will turn out to be 0, and hence the phi h of delta t would turn out to be phi hi delta t plus phi hq hi delta t, and this is 0, and then this is equal to phi hi delta t, or in other words, the correlation of the received signal is completely characterized by the correlation of the I components of the signal. Now this Bessel function, as we have derived in this, would look like the one that is present in this particular picture. So this is the picture, and we have also briefly shown you this particular picture, and it is clear now that what we have, this picture I was telling you last time, it should be a little bit modified, because this is a picture taken from book Stuber directly. So this axis, this x axis, is going to be fm delta t, and this axis is, as you are seeing, it is phi hi delta t normalized by omega p by 2, because omega p by 2 is the power that is normalizing this particular term. So this correlation function, as we are seeing, is decreasing from a peak value of 1 towards 0, and because of the assumptions that we have made, we are getting an oscillation, a damped oscillation about 0. So there might be negative values, but what is of interest, I mean, of course this is a model, so there are problems which come with a particular model. So what we would be interested fundamentally is in this range, where the correlation coefficient drops to very small values, and since this axis is plotted with fm delta t, we can use this particular figure for any values. For instance, if we change fm, because fm is equal to v by c times fc. So as we keep changing fc, or as we keep changing v, we will get different values of fm. So what we see over here is, as fm increases, so what we are basically getting is this is becoming smaller and smaller. So a particular value of coherence, means let us say this value of coherence, appears at a much smaller duration of fm delta t, or in other words, if fm is large, that means if we look at this product fm delta t. So let's read one point. If we take this line straight and we reach, let's say we reach this point, which is, let's say, 70%. So what we can read this as, at this value of fm delta t, which is, let's say, x x is equal to Fm delta t, the correlation is 0.7, or we could also state that phi hi let us say x is equal to 0.7. So, since x is equal to Fm delta t, as Fm increases, suppose we increase Fm, delta t must decrease in order to maintain the same value of x, so as to get the same value of correlation, and vice versa. So, that means as the Doppler frequency increases, that means as the velocity increases, the time at which there is 70% correlation would be smaller and smaller. So, what does it mean? This effectively means that as we increase our velocity, the time over which the channel is correlated to itself is becoming less. So, if we read this curve in another way, any point over here, let us say this is the point 9, let us say this point is 0.9, and we start going down this line, come here. So, this much duration of Fm delta t corresponds to that argument which would lead to 0.9 correlation. Now, if I divide this by Fm, what I am left with is delta t. So, delta t at which correlation coefficient is 0.9 is known as the 90% coherence time. Similarly, if I take this point and go down to, let us say, a point here, then this point has a value over here. So, we would have Fm delta t prime, which is another value of delta t here, because it is the same Fm divided by Fm would be t delta t prime, and for this case we would call it delta t 0.5. That means it is the separation in time which would lead to 50% coherence between the signal components. What it means effectively is that if we take the time axis is the t axis, and if we measure it at two instants t1 and t2, and if this gap between this time is t2 minus t1, which is delta t, right. So, if this delta t is equal to delta t 0.5, that means we are at this point the signal would be 50% correlated, and what we have made assumption over here, it is wide sense stationary. That means it is not dependent on T1 and T2, but it is simply dependent upon the lag time between T1 and T2. So, this is one of the very important things in the propagation characteristics, which one should understand very nicely. So, I would ask you to spend some more time in this, maybe spend time with the references that we have already mentioned, relook at it, try to understand it yourself again, because based on this the design of wireless communication system is done significantly. For instance, okay, so now we would say that coherence time is the time for which the phi hi in our case, which is hi delta t. So, basically we are talking about this delta t is equal to a certain value, let us say 0.9 or 0.7 or 0.5 and so on and so forth. So, these are very important, and remember the results we have got is because we have made one fundamental assumption that p of theta is equal to 1 by 2 pi, where theta lies in the range of minus pi to pi. So, if you change these assumptions, the results which we have obtained would be different. So, this particular derivation that we made, there was g theta p theta in this, and p theta was made 1 by 2 pi, because of which we had got this 1 by 2 pi over here, and we made g theta equals to 1, for which we arrived at this expression, and then we said if we would change those assumptions, these results would be different. So, whatever we are discussing is with respect to these particular assumptions. Any other assumptions would lead to different result. So, what we are essentially trying to say is coherence time is the time over which signal is correlated with itself. So, if this is the time axis, this is the h of t, signal what received would be fluctuating, right, like this. So, that is what we have seen, and we have been trying to get h of t, h of t plus delta t. This is what we have been trying to capture. So, that means we are taking reading at this point, and we are taking reading at some delta t, some increased delta t, and so on, and we have arrived at this particular expression. So, when we say a delta t 0.9, so that means we are talking about a separation in time over which the signals are 90% correlated. So, in this figure we would probably have the separation which is as small as this, which is probably as small as this, which is probably as small as this, where the signals are correlated with itself, right. If I have a point here and a point here, definitely the signals are not correlated, because we do not know at this gap there is uncorrelation. So, this duration of gap at which signals become uncorrelated would be a loose definition of coherence time, or the time separation at which signal becomes uncorrelated. So, there is a rule of thumb for coherence time which is mentioned as 0.423 by fm. So, if you use this particular formula, you would get a rough calculation of the coherence time for a particular signal. Little bit stricter definition of coherence time would be 9 by 16 pi fm. This is again a rule of thumb, but what is ideally to be done to calculate the coherence time is we should use this particular picture, that is the coherence time relationship, and as we have over here delta t fm, and we should say that suppose I want 90% coherence time. So, I would go to 90%, I would read this particular point, and I would try to come to the x axis. Once I have read this off, I know this is x, let us say. So, I would take x divided by fm to give me delta t. So, this delta t would corresponding to this value would give me delta t 0.9. For any other distribution, that means instead of taking p theta equals to 1 by 2 pi as we have in this particular expression, as we have in this particular expression over here, instead of p theta equals to 1 by 2 pi, if we do something else, in that case the curve would be different. In that case we will not get the Bessel function. In that case we will not get this Bessel function, it will be something else, and if we are looking at 0.9 coherence, we have to read off this 0.9, read this x axis. From this x axis we have to find out what is the coherence time corresponding to the amount of coherence that we require. This amount of coherence that we require could be 90%, could be 70%, could be 50%, whatever is the requirement. Effectively, what we mean by coherence time is the separation in time for which the signals are correlated to itself. So, beyond this coherence time, the signal will not be correlated to itself. So, if we take two samples, for instance, I take a sample here and I take a sample here, they are not correlated. If I take a sample here, they are not correlated. If I take a sample at this point and if I take a sample at this point, they are not correlated. Whereas, when I keep the time interval small, they are correlated. Now, on the same figure, if I would draw the situation where fm is very small, that means slowly fluctuating. So, in the slowly fluctuating case, probably the channel would vary in this fashion. In that case, the coherence time would be large, that means 90% coherence time could be achieved in this separation. So, here it could be 95% coherence. So, that means, if we look at very small separation distance, it could be 95% correlated to itself, whereas if we look at even larger distance, we may find 90% coherence. We may find 90% coherence at a larger distance. So, this is again an average value. This is again an average value, because this axis that we are looking at is phi h, which is expected value of basically in our case it is h I of t plus delta t. So, what we should remember is that every instance of separation of this delta t, we may not get 90% correlation, but on an average, if the separation is this T c, then you are going to get similarity between the values. So, with this we go on to a very important definition of our study. So, if suppose we have T s as the symbol duration. Symbol duration means we are talking of digital communication system. So, in a digital communication system, suppose we are sending symbols which are like this and so on. So, let this be the symbol duration. Okay. So, if the coherence time as we measure in multiple ways is larger than the symbol duration. So, what will happen? The channel at this point and this point would be correlated, because coherence time is larger than symbol duration. That means, across this time is less than coherence time. So, that means, channel is nearly flat, nearly equal to this. So, basically the channel could be fluctuating in this fashion, or in this picture if we look corresponding to the red line, the symbol duration could be as small as this. Symbol duration could be as small as this. So, if we have symbols going like this, then that is the situation that we are talking about. If we have this situation, then what we have is known as slow fading. So, we had identified the channel to be time selective. In time selective, if this is the condition, then we say it is a slow fading condition, whereas if coherence time is smaller than the symbol duration, that means the signal fluctuates even before the symbol is over. That means, the channel is fluctuating like this. In that case, it is known as a fast fading situation. All right. So, that means, once we calculate our coherence time, once again let me remind you, we could calculate coherence time using this formula, which is a little bit relaxed formula, or this particular formula which is little bit stricter. I would recommend you to always use this formula if nothing is mentioned. This is very, very important. If nothing is mentioned, if you use this, you are having a better margin and your system design would be better. If with this, it is basically the distance in time across which signal is uncorrelated. So, that was also okay, but it is not that tight design. Whereas, an exact design would be using the derivation of correlation function for the corresponding p theta, and from that you plot the curve and you read off the 90% coherence point, go to the x axis from which you calculate the time difference. So, from these three different ways you could calculate the coherence time, then you compare with the symbol duration. Once you find coherence time is larger than symbol duration, you know it is slow fading condition. If it is smaller than symbol duration, it is fast fading condition. Now, why it is important? Because clearly if the coherence time is larger than symbol duration, that means we have this particular scenario where the channel is fluctuating slowly. So, the channel is fluctuating slowly could be because of two possibilities. One, the symbol duration is really small, and the other is the mobility is very slow. In either of these two cases, you would get a slow fading condition, because we are doing a relative measurement, we are doing it with comparison, we are comparing the symbol duration with respect to coherence time. So, suppose symbol duration is 1 millisecond, let us say symbol duration is 1 millisecond and coherence time is 2 millisecond. So, if 2 millisecond is greater than 1 millisecond, it is slow fading, right. Now, you consider that this 1 millisecond is remaining same. So, suppose this is 1 millisecond and this is 2 millisecond. Now, using the same 1 millisecond, if there is increase in mobility, that means things start to move faster. If things start to move faster, the Fm goes up. So, if Fm goes up, that means you are shrinking the x axis. If that happens, then the coherence time reduces. If coherence time reduces, and as you increase the mobility, if coherence time becomes comparable or less than the symbol duration, you end up in a fast fading situation. Now, when you reach a fast fading situation, that means let us say this has become 0.5 millisecond. Now, when you are in a fast fading condition, that means signal amplitude fluctuates faster than the symbol duration. What is going to happen? Suppose I have sent x, there is of course noise at the receiver, and what we said is in a flat fading condition h gets multiplied. So, in a slow fading condition h would remain same throughout the symbol duration. So, I would receive the symbol y. If I could estimate h, then I could equalize the effect of h. For instance, x cap is equal to h inverse times y, and I would be able to recover x. That means, I would divide y by h and I would be getting back an estimate of x. Whereas, if the channel is fluctuating like this, that means, if I have y is equal to h1 times x for the interval let us say 0 to t1, and then we have h2 for the interval let us say t1 plus delta to capital T. So, that means, I am assuming there are two different two different notable values of h, one over the period of 0 to t1, the other over the period of t1 to capital T, that is the symbol duration or Ts. In that case, we have to have an advanced equalizer, sometimes known as a fractionally spaced equalizer, which would sample at a higher rate and would try to do fractional equalization or even more complicated procedures. So, typically we would like to design systems which would experience a slow fading condition rather than a fast fading condition. If you can't help creating a situation of slow fading, you would have to design advanced receivers which would be able to handle the fast fluctuation of signal strength. So, what we saw in this example is that even though the symbol duration has remained the same, as mobility has increased, coherence time has become smaller, and then the system from slow fading is experiencing fast fading. On the contrary, if we say the earlier situation where coherence time was 2 millisecond, I have a system which has a symbol duration of 1 millisecond. Now, suppose I use a different communication system. I use a communication system whose symbol duration is much larger. That means, the symbol duration is instead now let us say 5 millisecond. So, when symbol duration is 5 millisecond, although mobility is giving 2 millisecond of coherence time, it is experiencing fast fading. So, what we see is that the definition of slow fading or fast fading is comparison of coherence time with respect to symbol bandwidth. That means, if I am transmitting some information, let us take the example of GSM and LTE. These two systems have different symbol durations. So, these two systems will experience a different channel condition. One could experience slow fading, the other could experience fast fading for the same mobility condition. The coherence time, as you have seen here in this particular expression, is affected by Fm, which is the Doppler frequency. This Fm is a function of velocity, as well as it is a function of carrier frequency, as well as Fc. So, basically Fm is equal to V by C times Fc. That means, as I increase V, Fm increases, as Fm increases, Tc decreases, right, because clearly Tc is equal to 0.423 by V times Fc times C. That means, as I increase velocity, coherence time decreases, as I increase carrier frequency, coherence time decreases, right. So, as we increase mobility, coherence time would decrease. On the other hand, if I change my symbol duration, again although coherence time would remain the same, we would experience different kinds of fading condition. Okay. So, with this we move on to see what happens to other properties of the signal. So, what we would lastly like to see is the envelope correlation. Envelope correlation is basically the correlation of alpha alpha t. Basically, we are talking about phi of alpha alpha delta t, which is equal to the expected value of alpha of t times alpha of t plus delta t, where alpha of t is equal to mod of h t. Okay. So, the result that we have is what we are going to share with you over here. Again, the derivation is cumbersome, so we would not go through that. If you want, you can go through it. So, this expression this particular expression. Now, these results, these things are taken from Stuber. I have used the descriptions from Stuber. So, basically what we have is phi of alpha alpha delta t, this one would turn out to be pi of sigma p by 16 j 0 squared 2 pi f m delta t. So, what you see, the difference between the previous one and the current one is that it is j 0 squared instead of j squared. So, that means it is decreasing faster. Typical example of this would be the figure as shown over here. So, if you see this particular figure, this is the envelope correlation. So, this is decreasing faster than the other one, and if we look at the square envelope correlation, the square envelope correlation also gives us the same thing, that this is proportional to j 0 squared. Surprisingly, both the results give correlation to j 0 squared. Now, the importance of alpha and phi of alpha squared delta t, you can clearly guess, because alpha squared t is equal to mod of h t squared. Now, h t for s tilde t equals to 1, r tilde t is equal to h of t. So, basically this is giving us the signal strength, right. So, when we study the correlation of alpha squared, we are basically studying the correlation of the signal strength. So, what we have over here is that the correlation of the signal is proportional to j 0 2 pi f m delta t, whereas the correlation of the envelope alpha or the correlation of the alpha squared are both proportional to j 0 squared 2 pi f m delta t. So, this is the underlying thing that we should remember in this particular discussion. And just to summarize, what we have also talked about in today's discussion is the calculation of coherence time. We have explained what is the meaning of correlation function and how this correlation is affecting, and we have also explained a rule of thumb for calculating the coherence time for the special case that we are taking. The special case is defined by p theta equals to 1 by 2 pi, and finally, we have also described the fast and slow fading conditions, where we have said that the fast fading condition is when the channel fluctuates faster than the symbol duration, and slow fading condition is when the channel fluctuates slower than the symbol duration. So, it is quite easy to remember, when the signal fades at a rate which is slower than the symbol rate, it is a slow fading condition, whereas when the signal fades at a rate which is faster than the symbol rate, it is a fast fading condition. And with most of our analysis in this particular course, we will be mostly assuming a slow fading condition. That means, within the symbol duration, the channel is nearly constant and it is not fluctuating. However, from symbol to symbol, there is fluctuation of signal strength with time. Thank you.